We've already seen what central angles are, right? And we remember we took the definition of central angle essentially from what we had seen with the circle, because you can really only have a central angle when the polygon that you have can involve a circle, right? And that means generally you're speaking of regular polygons. So you take your regular polygon and you make sure that you can draw a circle that goes through all the vertices. And that's important because the only way that you can get a radius of a polygon is if you can have a circle that goes through all the vertices. Technically, there are other ways, but I don't want you to worry about those for right now. So in this polygon, this pentagon, I've drawn a circle around. I've got one radius here, but my definition for central angle needs me to have two radii, right? A neighboring one that I can form an angle with. So I draw another radius here. Radius, again, is from the center of the polygon to one of the vertices. And then I measure that angle, and that gives me the central angle. So that's your central angle in a polygon. But what we haven't talked about is calculating what that will be. Now, as it turns out, you guys have already heard the formula for calculating the central angle in a polygon, but you just haven't seen it applied to central angles. And it's actually the same formula for finding the exterior angle of a regular polygon. They have exactly the same formula. That formula, we'll see, is just 360 divided by the number of sides, 360 over n. So let's see why that has to make sense. First off, if you look at this one here, you see there's one central angle drawn in. If you picture all 5 central angles that this pentagon would have, together they'd make a full circle, and you'd have to chop them up into 5 to get 72 degrees for each one of them. Let's look at it in a little different way here. If you look at this diagram here, right now it's a triangle. And I don't know, it's kind of, there's a lot of stuff going on in this diagram. It's kind of a neat diagram. But you see here that the angle of this central angle in this regular polygon, it's an equilateral triangle, which is a regular polygon, is 120 degrees is the central angle here, which is what you would get if you were to take 360 divided by 3, divided by the number of sides. 360 over n would give you 120 here. If I add another side to this to make it a regular quadrilateral, which we usually just call a square, you'll see that the central angle here is 90 degrees, which is again 360 divided by the number of sides. There's 1, 2, 3, 4 sides. 360 divided by 4 gives me 90. That's also the same thing I would get if I were to extend this side and to measure the exterior angle. It would be 90 degrees here as well. Let's try with 5 sides. It's still going to be 360 divided by the number of sides, right? There's 5 sides. I've got 360 divided by 5 gives me 72. You can already anticipate if it has 6 sides, 360 over 6 gives you 60 degrees. If we go up to 7, 8, 9, 10 sides, I'm still getting a central angle here that's 360 divided by the number of sides. And that really makes sense because each side, right, has its own central angle. And so if you've got 10 sides, you've got to share up those 360 degrees between 10 slices of pizza. Each of them is going to have just 36 degrees. And again, if I were to extend this here to make an exterior angle, I would also get 36 degrees. That's why your formula for your central angle in a regular polygon is 360. Oops, let me actually get something here. 360 divided by the number of sides. Now, there isn't really such thing as a central angle if you're not dealing with a regular polygon. There are some exceptions to that. But this formula, 360 over n, for central angles only applies to regular polygons.